Cloud computing relies on a massive underlying assumption that multiple customers can share the exact same physical hardware without ever interacting. We build logical walls to keep tenant A completely isolated from tenant B, but occasionally those boundaries fail. A cross-tenant vulnerability happens when an attacker sitting in one environment manages to bypass those logical walls, reaching directly into the sensitive data or compute resources of an entirely unrelated customer. Google Cloud Platform has a specific structural quirk that creates exactly this kind of risk, and it stems from the naming rules inside Google Cloud Storage. Unlike local hard drives, Google Cloud Storage buckets require a globally unique name. Every organization on GCP shares a single global namespace. If a user registers a bucket named gs/test, that identifier is gone. You are permanently locked out from creating it. The globally shared, first-come, first-served architecture transforms simple naming conventions into a critical race condition to claim resource coordinates before an attacker can. This global namespace constraint collides directly with how GCP's managed services operate. Platforms like Gemini Enterprise, Cloud Run, and Vertex AI are built to execute complex tasks with minimal manual setup. To keep the user experience frictionless, these services don't ask you to manually configure backend storage. If a workload needs a staging area to move data, the service automatically provisions a bucket for you in the background. To generate a unique name on the fly, Google's internal scripts use a deterministic algorithm. They piece together known variables like your project ID, the geographic region, and the service name to construct the storage URI. The scripts check if the bucket exists. If yes, they dump data into it, completely failing to verify ownership. By predicting the URI and preemptively registering that bucket, an attacker commits bucket squatting. Your service blindly routes data to them. By implicitly trusting a globally shared namespace, GCP's automated services inadvertently handed data routing control to anyone capable of guessing a file path. Researchers at Focal Security discovered exactly how this flaw could be weaponized against Google's premium business AI platform, Gemini Enterprise, in an exploit tracked as GeminiSquat. Gemini Enterprise imports external data from internal sources, like Cloud SQL, to automate workflows. Moving that information requires an intermediate staging bucket. This chart shows the highly predictable string format Gemini used for these staging buckets. It combined the project number, the location, and the data source type. The location and data source type are standard, easily guessed variables. To complete the string and squat the bucket, an attacker only needed the target organization's GCP project number, which is readily accessible using basic enumeration techniques. Once the trap is set, the victim initiates a routine data import. The Gemini service checks the storage path, skips ownership verification entirely, and immediately dumps the organization's raw data into the squatted bucket. The attacker now possesses the raw contents of the organization's linked databases. Since they control the storage bucket, they can also modify this data before the AI processes it. Because Gemini Enterprise uses this ingested data to automate business logic, an attacker can inject malicious instructions directly into the dataset. This effectively bridges the gap between a storage leak and an active prompt injection attack. The stakes escalated with Cloud Run, Google's serverless compute platform. Cloud Run has a volume mount feature that syncs local container folders natively with GCS. Logic relies on the project number, service name, and region, terminating with the suffix compose volumes. Sourcing these variables requires almost zero effort. Every single component is broadcast openly in the text of the Cloud Run deployment's public URL. Unlike buckets holding static logs, these volume mounts interface directly with the active compute workload. Because the mount layer manages synchronization natively, any file the attacker places in the bucket appears instantly inside the running container. MountSquat provided an external attacker with real-time, bidirectional read and write access to the file system of an active, isolated serverless container. The highest severity exploit targeted Vertex AI, Google's machine learning platform. Tracked as VertexSquat, it affected the Python SDK used to save and load machine learning experiments. The SDK relied on a staging bucket pattern, combining the project ID, the string vertex staging, and the region. It suffered from the exact same absence of ownership checks as the other services. But VertexSquat is vastly more dangerous due to the payload. Vertex AI experiment artifacts are stored as serialized Python pickle files. Pickle is Python's built-in serialization format. It converts complex Python objects into a raw byte stream so they can be written to disk or sent over a network, and perfectly reconstructed later. This visualization shows the inherent security flaw of the pickle format. During the deserialization, or unpickling process, the interpreter automatically executes any code embedded within the file structure. The kill chain relies entirely on the victim. The attacker uploads a malicious pickle file to the squatted bucket. Later, an engineer decides to review their experiment and loads the artifact into their local machine or a Vertex notebook. The instant the victim's environment attempts to reconstruct the file, the hidden payload triggers silently, achieving remote code execution. This zero-click mechanism grants the attacker complete compromise over the host machine and the engineer's identity, securing a deep pivot point into the target organization. The commonality across these three vulnerabilities highlights a systemic failure in how multi-tenant storage logic is managed within GCP's service ecosystem. The operational advantage for the threat actor is massive. An attacker situated in tenant A can exfiltrate raw data or execute code in tenant B without needing stolen credentials, IAM roles, or prior network access. In practice, a threat actor could programmatically pre-register a vast matrix of predictable bucket names, blanketing hundreds of targeted organizations at once. Standard CI/CD pipelines and AI workloads inadvertently route sensitive traffic directly into attacker-owned infrastructure by following their default naming algorithms. The platform's own services act as the unintentional transport layer for the exploit. This impact matrix maps the vulnerabilities to the CIA triad. Through GeminiSquat and MountSquat, organizations faced an immediate, severe loss of confidentiality and integrity regarding their internal data and active file systems. VertexSquat completes the breakdown by compromising availability, granting an outside attacker total system access and control through RCE. The scope of exposure was enormous. Any GCP user deploying the default configurations of these three managed services was actively vulnerable. The zero-click, cross-tenant characteristics of the remote code execution drove the severity classification to critical. Following the research conducted by Focal Security, Google's vulnerability research program successfully patched and mitigated all three service endpoints by April 14, 2026. Google closed these specific vectors before they saw widespread exploitation in the wild, but the timeline reveals the inherent danger of relying on opaque managed services. While Google patched the automation layers of their services, the root cause remains. The globally shared namespace still governs Google Cloud Storage. This means custom applications and internal developer scripts relying on predictable naming conventions are still entirely vulnerable to bucket squatting. Effective mitigation starts with proactive developer hygiene. Engineering teams must preemptively provision expected default buckets, locking down ownership before a CI/CD pipeline ever attempts to run. Second, custom workloads must implement programmatic verification. Applications must utilize hard-coded IAM checks to strictly verify bucket ownership before routing any data. Architecturally, you can deploy VPC service controls to restrict perimeters, actively blocking data flow to unauthorized external buckets. Furthermore, utilizing domain-named buckets forces strict domain ownership validation, removing the predictable naming risk altogether. In a multi-tenant cloud environment, true security requires zero trust, even when dealing with the platform's own default automated configurations.